Good afternoon, everyone. Continuing our discussion of failure in static loading. We talked last time about ductile materials. Now we'll talk about brittle. I showed you the same slide last time. And we talked about the top group. For ductile materials, we have historically 5 different theories were put forth, and we now understand very thoroughly that 3 of them are discredited. 2 of them are all right, and we believe the distortion energy theory is the most accurate, well proven. Maximum shear stress is a bit more conservative, so that's acceptable if you prefer. Brittle materials, there have been 3 put forth over the years, over the centuries really, and of those we now know that 1 has a problem. The other 2 are acceptable, 1 being better than the other. So they're in order from no good to okay to best, top to bottom in that list. So you should not use the ones that are not marked with arrows. I showed you this the other day as well that describes 2 basic classes of materials that are materials will be either even or uneven. Defined as even, meaning it has virtually the same strength and compression as in tension, and uneven it does not. And typically uneven materials are stronger in compression than in tension. Any material will fail due to its weakest condition. So clearly uneven materials will fail in tension, and the ductile materials we found out yesterday, 2 days ago, fail in shear. Yes, Dan?
So, I mean, you probably just chose the scale arbitrarily, but are brittle materials generally stronger in compression?
Yes. Yes, that's what that's saying.
Well, I know in respect to one another, I mean, its own compression structure is technical.
In general, what Dan is asking, are brittle materials in general stronger in compression than in tension? And the answer is yes, most definitely. In fact, cast iron, gray cast iron, which is probably the most commonly used of these kinds of materials, is 3 to 4 times stronger in compression than in tension. Concrete's another example which has very poor tensile strength and very great compressive strength. I don't know what the ratio is. Concrete is obviously not a metal, and it's a material that I'm not sure we would dare characterize as homogeneous and isotropic if it has rebar in it, which most of the applications do. Then it's going to have very different strengths in different directions, right? Concrete without the rebar would be approximately homogeneous and isotropic, I would think. Yeah?
Did you say the other day during the casting process the material becomes weaker from just due to the amount of dislocations? Or
yeah, his question has to do with cast materials, and are they somewhat weaker because of the casting process? And the answer is yes. In terms of making pieces of metal for use, there's only a few processes available. One is referred to as wrought, W-R-O-U-G-H-T, which originally was the blacksmith taking the chunk of iron and making steel out of it by adding carbon, by essentially cooking it in charcoal. And once he had steel, then he heated it red hot and pounded it with a hammer. And he was making wrought metals, wrought iron typically. You see wrought iron decorative work on houses and buildings. So that refers to changing the shape of material typically when hot but solid, solid but plastic. In modern terms, this is done in a steel mill where ingots of steel will be run through rollers or dies and rolled into shape to make I-beams, C-channels, flat stock, round bars. Morgan Construction, which is almost across the street from the school, may still be the biggest supplier of steel mills. They were one of the pioneers in developing steel mill equipment. So that's wrought materials. Those tend to be fairly uniform internally because they're heated to red heat and then their shape is changed. And they never go to liquid. Cast materials are melted to liquid form and then poured into a mold and then allowed to cool. And as they do so, they develop a grainy structure in most cases. That's how they lose the tensile strength, because the grains are not well coupled to one another as they are when I squeeze that thing through rollers or whatever, right? So they have very different properties depending on how they're made. I should mention forging in the process of this discussion. Well, I don't want to make this a manufacturing class either. Got all this stuff on our plate. But I can make a part as a casting and then machine it. I can make the part from what's called billet, B-I-L-L-E-T stock. That's a chunk of metal I buy at the store, which might be round, square, and cross-section, might be I-beam, might be whatever. Actually, I-beam wouldn't be a billet. Just a solid chunk, usually long and some dimensions. And I will put that in a series of saws and milling machines and lathes, and I will take material away until I have what I want left of the part, machine it. That's a relatively strong part compared to a casting. The strongest that I can make a part in metal is to forge it. And by that is meant I make some very expensive and very elaborate dies in steel, in hardened steel, that are shaped like the part I want, but probably not like the final shape, because I got to go at this in stages. This is doing what the blacksmith did with a hammer, but with machines. So I'll have a series of 3 or 4 dies that take that part from a chunk to gradually to its final shape. And this process is used where parts are very highly loaded. Think aircraft landing gear struts, for example, would be a good candidate for forging. And what's happening is I heat the thing red hot and I beat the dickens out of it with a die, which amounts to a big hammer. And I flow that material into the shape of the part. As a result, the grain follows the shape of the part. And thus I get higher strength than if I take something that's made as a long, round bar, which has grain running the long way, and I now cut it up, and I cut across the grain, and I have exposed end grain pieces and so on. Now, they probably will machine the forging to put holes in it and such, but the main body of the part will remain as forged, most likely. And that's the strongest way I can make a metal part. Wing spars for aircraft are forged. Wyman Gordon in Worcester, I guess they're now only in Grafton. They fell on hard times and lost their Worcester plant. They pioneered forging of aluminum and titanium for aircraft. They were a big supplier to the Air Force and the military aircraft manufacturers for years and years. So that's kind of getting off topic. So back to failure theories. So I show on the right stress strain curve of a brittle material, and you can tell it's brittle. There was a question on your test of this sort, because it doesn't have very much beyond the yield point. In fact, this thing doesn't even have a straight section. And that's probably cast iron, because not all materials obey Hooke's law, which says that stress is proportional to strain up to the elastic limit. Wrought materials, wrought metals do. Cast metals don't necessarily do that. So we have to fake it with an approximate value for Young's modulus, shown on this offset line, by going over 0.2% in strain and then drawing a line parallel to the starting slope here, and find the intercept and declare that to be the yield point, because there's no distinct yield point, unlike the ductile materials that really give and show you that little hump as it starts to go into the plastic zone. This doesn't really have much of a plastic zone. The plastic zone, such as it is between Y and F is fracture. So brittle materials just suddenly break, as opposed to giving us some warning, as with our specimen over here for the ductile steel tensile test. You can see the necking down that occurred as it went beyond the yield point and on the way to the fracture point. And so you have visual warning that it's going, if you happen to be looking in the right place at the right time, and you can run, right? But the cast specimen over here just breaks with no necking. So it goes essentially immediately to the fracture point. So the tensile load, tensile stress diagram, Moore's circle for the tensile test in the brittle material looks just like the one for the ductile material, but the material is behaving in a different way. Notice how close the ultimate tensile strength is to the yield strength, and that's not true of soft ductile steels. There'll be quite a difference between those two numbers, maybe 30,000 to 50,000 psi for a 1020 steel or something like that. There's the same picture of the specimen I just showed you on the board with a before and after being pulled. That's cast iron, gray cast iron. Another word on materials, which it's critical you have a good understanding of materials to be a design engineer, because you've got to make it out of something. There is cast iron, there's cast iron. When you just see the term cast iron, that usually implies it's what's properly called gray cast iron. And that's the stuff that you see made making machine bases and things like that. It's very weak in tension. 20,000 psi tensile strength, good compressive strength. Not generally used for machine parts that are loaded dynamically. But I can all go to a better grade of cast iron called cast ductile iron. And that's made by a slightly different process and has different chemical composition and has significant tensile strength up to about 100,000 psi. On the other hand, wrought steel can go as high as 300,000 psi in tensile strength with appropriate treatment. So there's still a big gap between wrought, really strong, and cast, not so strong. Now, here's another interesting pair of samples. These were done in a torsion test. In other words, notice that the samples have square ends, these two guys right here. And that's so you can put them in something that can rotate them about their own axis, to twist them to death, right? Notice the yellow line painted on the sample? The one on this side had a straight line on it before the test began. It now looks like a barber pole, because that wrapped up looks like several revolutions before it finally let go. That's ductile steel. So it yielded quite a lot before it finally fractured. Look at the fracture surface. What's the direction of it compared to the tensile test? Can you see it from where you sit? You can see it on the board above me. The left is ductile. The right is brittle. Why are those surfaces at different angles? I didn't quite hear you. It sounded like you said the right thing there.
Does the ductile steel fail in tension first and brittle fail in shear first?
It's just the reverse, but you're on the right track. Where is the stress in this part? Think of the stress cube. This is in torsion. What kind of stress is being generated in the material? Shear.
Oh, right.
Right?
Yeah,
You had the right idea. Yeah. No, I think you understand it. That it's loaded. This is my Necco wafers, right? My stack of Necco wafers, and they're all getting twisted versus one another. And so it breaks along the shear plane because ductile materials are weakest in shear. But now, the guy on the right is cast iron. That's brittle. It's weaker in tension than it is in shear. The stress is still the same. It's on the Necco wafers doing this, but it breaks on a 45-degree plane because the tensile and the shear are always 45 degrees apart in the principal stresses. Yeah? So it's just the reverse. This is what was confusing you. This breaks at 45 degrees because I'm applying tensile stress, which is straight across, but it breaks in shear, and this breaks in tension right across. See the difference? So there's the Moore's circle, and we just answered that question, right? So you have equal shear and tension in a pure torsion case because your Moore's circle is centered on the origin, right? And thus, the weaker one will dominate. And if it's ductile, it breaks due to that stress. If it's brittle, due to that stress. So here are the failure theory envelopes. This is analogous to that ellipse we looked at the other day, but it's obviously not an ellipse. 2D case, the 3D case exists as well, but it's harder to plot. So let's look at 2D. And I've got sigma 3 and sigma 1 on the two axes. And those axes are truly 90 degrees apart. This is not a Moore's circle. So those are the principal stresses. And if it's a 2D case, the sigma 2 is 0. So we don't have to look at it, right? And we're plotting here normal ultimate tensile stress. SUT is ultimate tensile stress. SUC is ultimate compressive stress. And being an uneven material, they're very different. So the compressive side, which is negative, is much bigger than, and downward is negative. Positive is small. So there are three different, actually four, the way I've set this up. There's four different arrangements shown here. Normal stress theory for uneven materials would be the outside box, which has gray primarily in it, but it's overlaid with the pink in the middle. So the outside gray box, which is a rectangle, actually it's a square that's not centered at that origin, is the normal stress envelope, right? SUT, SUC. If I have an even material, its corresponding box would be the dotted square, because now I'm plus or minus the same number, same concept. We showed the other day that that dotted envelope is unsafe for ductile materials, right? And that the ellipse was within it. The Coulomb-Moore I'll take next. The Coulomb-Moore theory is the right top corner of the normal stress, but then a line drawn from the sigma 1 axis intercept down to this intercept, and it's the light pink. And the modified Moore includes the darker pink. So why do we get these lines? Where do they come from? We need to look at the test data. So if you look at the right panel here, you see little dots which are where the parts failed under different combinations of stress. So somebody gave it a sigma 1 of that amount and a sigma 3 of that amount, and it broke there. And another one broke at a sigma 1 of that amount and a sigma 3 of that amount, et cetera, et cetera, et cetera, et cetera. So you can see that they're fairly close to that little square corner up there, and they're okay down to minus SUT. This is out of a different book where they don't differentiate, as I do, between strength and stress. He uses sigma for everything. So sigma UT is my SUT, and sigma 3 is a stress. And the breaks start to come inside this outer rectangle or square, which is the maximum normal theory. So that's why it's not safe, because some parts break within its bounds. But notice that all the breaks are outside of that dotted line that I just pointed out, called the Coulomb-Moore theory. And then later on in time, more test data, people said, well, really, the breaks are all outside this line, so we could afford to run this piece of the normal stress line down to here and then back down to the corner, and we have more area to say is safe, okay? So that's considered to be the most accurate model for failure with brittle materials, but which is analogous to the distortion energy theory for the ductile case. But if you want to be conservative, you could use that Coulomb line, and you've got a little bit of extra margin, and that's analogous to the maximum shear hexagon in the ductile case, which is inside the enveloping ellipse, okay? So I think I've answered these questions already in my discussion. You tell me, based on what I just told you, which theory best fits the experimental data? All together now. Got it. Conservative is Coulomb-Moore, and lousy is normal stress theory. Don't use it, because some of your stuff is going to break, and you will think it doesn't. Now, these, of course, are actual fractions, so we would not go that close to it. We would put in a safety factor, which gives us an envelope inside of that, of the same shape, by whatever comfort margin you want. factor of 2, 1.5, whatever you like. Same picture. Notice this little line says torsion. Well, torsion will be equal positive and negative normal stresses, right? Because the Mohs circle is centered at the axes. Shear plus and minus. I got equal plus and minus normal. So any torsion case is on a 45-degree line, either there or there, depending on directions. So that's the modified Mohr boundary as labeled. And that just reinforces what the previous slide said. Now, this is the right half plane of that same diagram we just looked at in the previous slide. And the title at the top says, for 2D cases, we only have to look at the right half plane, provided that we, for this diagram, since I show sigma 3 and sigma 1, it has to be for the situation where I have ordered my principal stresses, as I suggest in chapter 4. They're always ordered algebraically, largest to smallest, and sigma 2 is going to be 0, and I'm only looking at sigma 1 and sigma 3, so I don't have to plot sigma 2 at all. So this is sufficient to satisfy all cases that I'll encounter. So this is referred to as the plus-plus quadrant, the first quadrant, and this is the fourth quadrant, which is the plus-minus quadrant. And I can then see, if I'm inside this green line, I'm safe, and the degree to which I'm safe, if this green line represents failure, would be the ratio of the length to A prime divided by the length to A, right? And I could also write an expression that said the leg of that triangle to A, this little dog leg here, divided into the leg of this guy, which is, of course, SUT. That's the same ratio, isn't it? In other words, if I keep increasing the stress with the same ratio between sigma 1 and sigma 3, I'm going to keep going up that line and pop out at A prime. But I can get the ratio with either of the components, either the vertical component, that rise divided into this rise is the same ratio as that run divided into this run, right? By symmetry of triangles. So I have three possible cases here, shown as A, B, and C, in terms of where I would break out a prism. So if I'm up in the first quadrant, my breakout is always via A prime. If I'm in the fourth quadrant down here, depending on the relative values of sigma 1 and sigma 3, I could break out of the vertical piece of the modified Mohr or break out of the angle piece. So I have to differentiate between those two cases. And they're going to be identifiable by the relative values of sigma 3 and sigma 1, right? If I'm down here at point B, if sigma 1, or rather if sigma 3 is less than or equal to sigma 1, then I'm going to break out either above B prime or at B prime, right? If they're equal, I'll come out at B prime because it's 45 degrees, right? If sigma 3 is less than sigma 1, in terms of absolute value, this would be, then I would, because sigma 1 is positive and sigma 3 is negative here, I would go out somewhere in here. And if sigma 3's absolute value is larger than sigma 1, I'm going to break out of this line. So I have to write the equations for these lines to get the safety factors. So if I'm in zone 1, it's very simple. Safety factor, which is often just called N, is simply the ultimate tensile strength divided by my largest normal stress, principal normal stress, sigma 1. So this is quite simple to use, provided I get the right numbers in it. So that's my case 1 or zone 1, where I'm either my sigma 3's absolute value is not larger than my sigma 1. If I'm in zone 2, which is the south part of that piece, then I have a more complicated formula, and these come out of equations for those lines, and I derived those in the book so you can see where that equation comes from. So now I'm down at either B or C. Actually, I'm down at C in this case, so I'm below here, and I'm going to come out on this angle line. So you need to understand the difference between these cases so you go after the right formula. And it's based on the relative values of your sigma 1 and sigma 3, as well as their signs. Now, we have this very neat concept in the ductile theory called von Mises, or von Mises-Henke, or Charlie's, or Harry's, or Sam's, whichever name you want to take, from all its inventors. Okay? And that's a very nice way to sort of wrap everything up with a ribbon. I got some kind of crazy stress state. I can calculate the principal stresses for that. Now I can take the principles, put them through the meat grinder, and come up with a von Mises, and I can compare that directly to my tensile test specimen number and say whether I'm safe or not, right? That's very convenient. So we didn't have until recently an analogous situation for the Brittle case until Norm Dowling of Virginia Tech, who has an excellent book on this topic from the materials side. He's a materials prof at Virginia Tech. And I referenced a lot of stuff from his book in here with permission. I think those pictures I was showing you are out of his book. And he came up with this interesting concept. He creates these factors, calling them C1, C2, and C3, which are functions of the stresses that you happen to have. And this, of course, works now for 3D, because I've got all three of them in here. So C1 involves sigma 1 and 2, C2, 2 and 3, and C3, 1 and 3. So you got all your bases covered here for a three-dimensional stress state. And you have the ultimate tensile and the ultimate compressive strength of your uneven material. So I can calculate those based on my particular set of principal stresses and my material strengths. And I can then apply those, and I think he gave it this little symbol. I think that's called the cedilla. Does that sound right? A little squiggly over the letter. I'll call it a cedilla. I don't know any better. So sigma cedilla here is, I'm calling it Dowling's effective stress. He doesn't call it that, but I do. So Dowling's effective stress, analogous to von Mises, with this funny symbol over it, is found by taking the largest value of all 6 of these parameters. You already have 3 of them, sigma 1, 2, and 3, that you calculated. And you use his equations to get these other 3, C1, C2, C3. And the biggest one of those is this sigma squiggle. And I divide that into SUT, and I have a safety factor. Okay? So this I can computerize. So in my program, I can simply set these equations up. I can have it calculate all 6 of them. I use a max function to find the largest one. I grab that number, divide it as SUT, and there's my safety factor. Very convenient. Okay? If the max comes out less than 0, in other words, everything's compressive, then you set it to 0. I'm going to change topics completely, so I want to pause here and see if you have any questions on what I've just put forth. Yes?
But if it's 0, then it won't be SFB. What's infinity? Will the safety factor be infinite?
Yeah.
So if it's
Well,
not compressive, then
we don't worry.
if brittles are very strong in compression.
It's not only strong, but these failures are all the result of cracks growing, which is what we're going to talk about when I resume the slides, okay? So it's a cracking process, and that's true whether it's ductile or brittle material. And when you pull on a material, if there's any cracks there, you're tending to open the cracks and make them bigger, and eventually they get big enough to break. But when you compress, you're smushing the cracks together. So you don't allow the cracks to grow in compression. So when we get next week to dynamic loading, you'll hear me make a statement such as this: all failures are due to tensile stress. If you don't have tensile stress, you don't have a fatigue problem. It turns out that compressive stress is our friend when we have fatigue loading, because it closes the cracks and prevents them from growing. And I'll show you techniques by which we deliberately introduce compressive stress into a part when we make it as a protective shield against the tensile stresses we know it's going to see in service. And there's several ways I can do that, and they're very effective. Okay? Good question. So tensile and shear are our enemy. They work together, depending on the material type, to destroy the part in some fashion. Okay? Any other questions on this? Okay. New slide, literally. Very interesting topic called fracture mechanics. And I'll set this up with some history, which I think is quite interesting. First, the intro says that modified Moore we just talked about makes one very basic assumption, as does the distortion energy theory, and that is that the material has these properties. It's homogeneous, same throughout, and it's isotropic, just as strong in the x and the y and the z directions, no difference. Okay? We also believe, with good evidence, that all materials contain microcracks, so tiny you can't see them with a microscope, that provide stress risers, stress concentrations, and those will raise local stresses. I've shown you that sharp cracks have a stress concentration that goes to infinity. The hole in the plate, if you take the ratio of the height of the hole, height of the ellipse to the width to 0, thing zooms off to infinity. We have many, many examples, I'll talk about a few of them, of sudden and catastrophic rupture of parts with obviously disastrous consequences. Fracture mechanics theory, which is only about 60 years old, just a pup by my lights, finally figured out what's happening here. So let me show you some examples of what was happening that was initially very mysterious. What this says, I'll paraphrase it, back in World War II, 1941-2, when Pearl Harbor happened, and we got into the war in a big way, we'd already been sending Lend-Lease over to Britain because they were already under attack by the Germans for 2 years. And we needed ships. And of course, after 41, we needed tanks and guns and a whole bunch of other stuff. But initially, it was ships to ship materials over and later troops. So they started on a campaign called the Liberty Ship Campaign to build ships for our liberty. U.S. government funded the bill, right? And so shipyards sprung up like mushrooms all over the United States, and they devised new ways to make ships so they could make them in a hurry. Now, up until that time, all through the 30s, the way you made a ship of steel was you riveted the plates together. So you bunch of plates, you put holes in them, and you rivet them all together on the seams, and that's time-consuming and labor-intensive because some person has to go there with the rivet gun and pound the rivets in, red hot, and all that stuff, right? So somebody came up with a bright idea and said, what? Welding's been around a while. We don't know a hell of a lot about it, but why don't we get rid of the rivets and weld the ships together? Great idea. So they started welding ships together, and they were making them like one a week in the same shipyard. This is important. The hull was welded ductile steel, very ductile steel, low carbon steel. 12 of these ships split in 2 before they ever left the pier. Approximately 100 more split in 2 in the middle of the North Atlantic, full of crew and goods. Most did not sink because they were bulkheaded. So 1 ship left port and 2 arrived, 2 halves. They would somehow get them to Britain. If they didn't sink, they'd get them to some neutral or friendly country. They'd weld them back together again and send them out. There's a picture. I think that's the SS Schenectady. It was built in Oregon, Portland, Oregon, Jan 16, 1943. And what they would do is they would weld the hull up in a dry dock until they had it watertight and have a deck on it. Then they would launch it and tow it around to a pier where they would then start to put the guts in it, put the engines in and all that stuff, right? So they could free up the dry dock to make another one. So this had been towed from the dry dock over to a wharf, and in 24 hours, it broke in 2, like that. Now that looks like a brittle fracture. It doesn't show any necking. It didn't get longer before it broke. It just broke, as if it were brittle steel, but it wasn't. So this caught a lot of people's attention, as you might imagine. And the U.S. government created this Ship Structures Committee, which still exists to this day. I've talked to them. I got that picture from them. Once the government creates a committee, it never goes away. Here we are in 2011, and they're still in business in Washington. Don't ask me what they're doing now, because they've solved this problem. But as a result of the government's huge effort in setting researchers all around the U.S. university system working on this problem, it took till the war was over to figure it out. It was something like late 40s or so when the theory finally was put together. And that's what I'm going to discuss with you today. Here's another example, much more recent. This is NASA, and it's a rocket body. I think it's a Saturn. It doesn't really say. And what they would do to see if these were safe to put rocket fuel in and launch was they would pressure test them once they had the shell complete, and they would do that by putting water in them and then maybe pumping air pressure on top of the water. I'm not sure exactly how they did it. But the spec called for it to withstand 960 pounds per square inch. They got it up to 542, and that happened. Now look at that picture carefully. You will see people in it. To give you an idea of scale. The thing's huge. And it's like an egg cracked, just like that. Another example. My father told me this story because he was alive and living in Boston in 1919. And he told me the story, and then I ran into it again in 1994. My clock radio was set to NPR News, as probably many of yours are too. So I wake to the news every morning. And on the morning of January 21, 1994, 75 years to the day after the Great Molasses Flood in Boston, I heard the following story. They interviewed a 91-year-old Boston man who was 16 years old in 1919 and lived somewhere in the neighborhood, the North End. He recalled a sudden popping sound like machine gun fire, followed quickly by a loud explosion. The machine gun sound was quite likely the sound of the crack propagating across the tank wall at up to a mile per second, which is what that rocket case did and what the tanker did. I failed to mention that earlier. And the loud explosion was probably that of the molasses pressure bursting and disintegrating the tank, large pieces of which landed on and destroyed Mrs. Murphy's boarding house hundreds of yards away. I actually went to the Boston Public Library years ago and looked up the newspapers for that day and the week thereafter and read a whole bunch of stories, because it was all over. Boston had 10 newspapers at the time. That's the whole, they were all on that story. These are my words, my recollection of what the guy on the radio said. So what happens in these fracture mechanics failures is really dramatic. It's a crack growth problem. So you have to have a crack. You start with a crack. But everything has cracks. So there's always the seed there, okay? You put some stresses on it of some sort, and the crack grows. And slowly it grows, and slowly it grows, slowly it grows. Then it gets to a certain length such that the material left is not enough to hang on anymore. And it crosses what's called the fracture toughness threshold. And the thing unzips at a mile per second through the metal and just comes apart. So, getting into the theory a little bit here, I'm not going to go into this in great detail. You could do a whole course on fracture mechanics. And there is a higher level course in materials here that deals with this, if you're interested in it. So they talk about 3 modes, 1, 2, and 3, and it depends on how you're loading the parts. So mode 1 is a pure tensile kind of loading. Here's the crack, and something's causing the crack to open and close like this, okay? And the other, number 2, is shear, which trying to shear the crack, and number 3 is sideways pulling on the crack. I'm only going to talk about mode 1, because we can get the idea from that. So here's that same picture I showed you with something added. This is the ellipse crack and plate in tension. And what they understand now is happening is at the crack tip, you're going to have very high stresses. They're going to go above the yield point, and you're going to develop a plastic zone around the tip of the crack. And that relieves the situation temporarily, right? Because now it's redistributed the stress. You have, it's not literally a puddle, it's not melted, but it's gooey plastic zone material around that. So it has relieved the stress locally. Back to the other slide. So these equations that you see allow you to calculate the magnitude of the sigma xy and tau xy around the tip of the crack, with theta being the angle as you go around the crack. And K is the stress intensity factor, which is defined as your nominal stress, which would in this case just be F over A. And they don't even bother to subtract out the crack. It's just F over A for the whole section. It wouldn't make a big difference because the crack is tiny. And that's your sigma nominal. And then it's times the square root of pi A. And A is a dimension over here. It's the half dimension of the crack. Okay? And beta is an adjustment factor which varies depending on the geometry. So if you go to a fraction mechanics book, which this does not purport to be in any sense of the word, it's just a brief introduction, you will find chart after chart of the beta factors for this, that, and the other, much like your stress concentration factors in the back of this book, right? So I can look up the beta. I can calculate my nominal stress. Pi I already know. I have to make some guess or measurement to find out what A is. Get K. So this is, it's not stress, it's a stress intensity factor. It has weird units. The units are megapascals times meters to the 1/2 power, or thousands of psi times inches to the 1/2 power. Wacko units. So it's not a stress unit, but it's calculable. And so what I'm doing here is I'm plotting the von Mises stress as I vary theta, take a little trip around the crack tip, theta from 0 to 360, and I get this mustachio-looking thing, and it has peak values at 71 degrees and 71 back of 360. And if I then set theta to 71 degrees, and I move away from the crack, notice there's an R in there someplace. Where was the R? R is in this equation right here. That's the radius away from the crack. That's this little vector right here. So as I move away from the crack, of course, the stress gets smaller, right? So it's in the denominator. So this plots sigma prime von Mises at the 71-degree angle, which is the worst case over here, and for a logarithmic plot from a distance, a radius of 10 to the minus 6 meters or millimeters or whatever units you're working in, through 1,000 to 1. So 1 radius away, it's essentially gone to 0. And that's what gives you this plastic zone close to the tip. Does that make sense to you? Have a picture of what that's doing? Okay, so now we can calculate by some means this K value, this fracture stress intensity factor. But we have to have a strength type factor to compare it to. So we need another parameter. And it's given the name K sub C. That's actually I've shorthanded it a little bit. I have some explanation up here. It's called the fracture toughness, K sub C. That footnote in the book says there's really 3 of these, one for each loading case. There's K1C, K2C, and K3C. And I'm only looking at K1, so I dropped the 1. So this is really K1C. But for simplicity, I called it just KC. So the deal is, when the value of K in these funny units, megapascals times meters to the 1/2 power, reaches KC, it unzips. And it's gone in a second. Comes apart. So my safety factor wants to be some comfort zone away from that. Don't let my K get anywhere near this number, right? Now, several of you have already told me that you do fly. Commercial, I would assume. Anybody a pilot? Private pilot? You are? You might want to take a close look at your plane before you get in it next time, because all aircraft, all commercial aircraft in the sky have cracks, and they're growing. You see why it's not good to be an engineer if you fly? And to make matters worse, they're made mostly of aluminum, which is not that strong and does not have an infinite life possibility, which we haven't come to. That's next lecture, probably. So there's a whole bunch of issues that can lead to a piece of an aircraft unzipping, and it has happened more than once, and falling from the sky. And so to prevent this, now that we know what is happening, what's doing it is the fractured mechanics problem, okay? And the cracks are developing slowly, we hope, and getting bigger and bigger, but at some point they're going to get to the danger zone. So the FAA requires every N hours, I've forgotten what N is, maybe 1,000, you might know, 1,000 hours? There's some particular bogey of flight time. Say it's 1,000 hours, probably not the right number. Every 1,000 hours, that plane has to be brought into the shop, and certified aircraft mechanics go through it, and they're supposed to X-ray, inspect, crawl into the wings, look for cracks, measure the cracks. They have formulas to apply them to, and you take the crack length, and you calculate these numbers, and you see how close are you to failure, and if you get within the bad zone, you're required to take that airplane out of service and either replace the part or do some kind of repair, okay? So this is just a table of fracture toughness values, this K sub 1C. I was calling it K sub C on the previous slide, for various materials, and there's much, much more of that information available in the literature. By God, I'm going to finish on time today. This is my last slide, I think. That picture's in your book, and the part's in my hand. I'm going to pass this around. If time doesn't permit, you can inspect it on the way out. It's worth a look. This is a trailer hitch. The ball goes there, the hole for the ball. And there was other stuff here that was cut off. So this would be on some kind of bracket that gets bolted or somehow fastened to the back end of the car, okay? The story behind this is that I taught this course one year, many years ago, right here, and it was springtime, I guess, and the student went back home to Washington State, Oregon, someplace out there, for the summer to work in his father's business, and his father made trailer hitches. He had like a welding shop, I think. He was sort of a blacksmith. And one of his products was to make trailer hitches. And the next September, the student shows up in my office with this in his hand. He says, my father was making a trailer hitch, and what he does is he takes, this is a piece of wrought steel, run through a mill to make a rectangular thing straight. Heats it up red hot with a torch. It's in a vise. Puts a pipe in the hole and bends it 90 degrees when it's red hot. This one broke when he bent it. And you can see it pretty well in the photograph. Maybe you can't. You can see it over here. This surface looks like a brittle failure. Does not look like a ductile failure. This is ductile 1020 steel. And it was red hot, which makes it even more ductile. It's out in the plastic zone. And it cracked instantly in a brittle-like failure. And when you handle it, it's sharp on the edges. Don't cut yourself. And look at the brake surface, and you will see a little smiley there, which is a crack. And that piece of steel happened to have a crack in it. And when he grabbed that, put that pipe in the hole, and did this, he exceeded the fracture toughness threshold, and bing, it came apart. And you would never expect ductile steel to break like that, especially red hot. That's what killed the Liberty ships. They came apart as if they were brittle. It turned out after much more investigation that the culprit was, I don't know if it was that Schenectady in particular, but in one of the, I read a lot of documents from that ship structure committee, and one of these studies said that a welder had erroneously struck an arc, while he's moving his torch around. He hit an arc on the deck and put a little gouge in it, a little crack. And that's where it started. And it came unzipped across the deck because of that little little nick. That was the crack that started the whole thing. So once they didn't really understand it until after they stopped building Liberty ships, unfortunately. But modern shipbuilding, I would hope, is taking this into account. Yet I am told by some merchant mariners of my acquaintance that current merchant marine ships, and I think also Navy ships, do develop cracks to this day. And what do? They weld them up and send it back out. All right. Any questions on this? Now you know that engineering is really interesting and fun. Scary too.